AI broke the internet again, and this batch is absolutely stacked. A humanoid robot just learned to dance, do backflips, and dig trenches. Zero prior training on any of those tasks. Google DeepMind just won the CVPR Best Paper for building a model that watches a video and reconstructs the entire 4D world inside it. And someone just released GitHub for robots. We've also got a TTS model that removed discrete tokens from the pipeline entirely and hit state-of-the-art in 3 languages. NVIDIA built a system that edits your video in real time at near 1080p on a single consumer GPU. Microsoft's new voice model generates a 90-minute 4-speaker podcast with background music, emotional arguments, and spontaneous singing from text alone. Plus, Stable Audio 3, Holo 3.1, Quen ImageBench, and a few more. So, let's jump right in. First up, NVIDIA's SANA team dropped SANA Streaming, and this one is specifically about real-time video editing at high resolution. Quick context. The original SANA was a highly efficient image generation model based on a linear diffusion transformer. SANA Streaming takes that and applies it to a completely different task, video-to-video editing in real time. The goal is live broadcasting in gaming scenarios where you need to transform an ongoing video feed according to text instructions while it's running. 3 technical pillars from the paper. First, a hybrid diffusion transformer architecture. Softmax attention in some of the blocks for better local modeling, linear attention in the rest for efficiency. Second, cycle reverse regularization. A novel training strategy where the model learns to predict the original source frames from its own generated content, which forces semantic consistency over time. Third, the system is designed for streaming, bounded memory use, and real-time throughput maintained continuously. The target resolution is 1280 by 704. That's above 720p. And it runs in real time on a single RTX 5090. That's the key claim. Minute-length video editing at near 1080p equivalent quality without needing a render cluster. For context from the broader SANA family, SANA Video could generate a 5-second 720p video in 36 seconds on an H100 and is 13 times faster than WAN 2.1 for 720p generation. SANA Streaming pushes this further into the real-time editing use case. The playground is live at sana.handlab.ai. GitHub is open. If you're interested in reading further, I'll link to the project page in the description below. Also this week, H Company released Holo 3.1, their computer use model family, and the upgrade story here is about deployment flexibility. So Holo 3 was their original state-of-the-art computer use model, browser and desktop control. It got adopted fast by developers building automation workflows. But as teams moved from evaluation to production, they kept hitting the same problem. A model that performs well in browser control doesn't automatically transfer to mobile or inside a different agent framework. Holo 3.1 fixes 3 dimensions. Mobile automation. On Android World, the standard mobile automation benchmark, the flagship 35B model jumps from 67% to 79.3%. The smaller 4B and 9B variants go from 58% to 71%. That's a substantial gain on mobile specifically. Cross-harness performance. Holo 3.1 now natively supports function calling protocols alongside the JSON output already in Holo 3. Across OS World and their internal benchmarks, covering e-commerce, business software, and collaboration tools, function calling and native execution now perform at near parity. Also a 25% plus improvement over Holo 3 inside their own HoloTab harness. Local inference. First time. This is their first release to ship quantized weights, FP8, Q4GGUF, and NVFP4 for the 35B model. The NVFP4 variant delivers 1.41 times the token throughput of FP8 and 1.74 times that of BF16. On DGX Spark with NVFP4, GPT-4 plus their harness optimizations, average step time drops from 6.8 seconds to 3.3 seconds, a compound 2x speedup. The Q4GGUF runs on consumer Mac or Windows hardware, fully private, nothing leaving the local network. Model sizes: 0.8 billion, 4 billion, 9 billion for cost-effective local deployment, 35 billion-A3B, all on Hugging Face. If you're interested in reading further, I'll link to the release page in the description below. Also, this week, Stability AI just launched Stable Audio 3, and the main thing they're calling out here is the data licensing story. Stable Audio 3 is trained entirely on fully licensed data. That's the lead. They're positioning this as the foundation for what the audio community builds next, specifically because commercial derivatives built on it have a clean licensing story. It's a model family, not a single model. 3 of the variants are open weights and available for download on Hugging Face right now. The 4th is available through their commercial API and the Stable Audio web app. The demo on their official page gives you a real sense of what the model can do. One of the example prompts they show is a 1980s summertime acid jazz track, and you can click play directly on the page and hear what that generates. They call it Coastline Cassette. The awesome thing is, the open weight models are free to download, fine-tune, and build on. If you're interested in reading further, I'll link to the Hugging Face collection in the description below. Also this week, DOTS.TTS from the Red Note AI Lab. And this one is genuinely architecturally interesting. So most TTS systems use discrete audio tokens. They take audio, convert it to a codebook of tokens, then train the model to predict those tokens and decode them back to audio. The problem is that compression step loses information, and the resulting audio often has subtle artifacts or loses naturalness. DOTS.TTS removes discrete tokens from the pipeline entirely. It's what they call a fully continuous, end-to-end, autoregressive system. The architecture? A semantic encoder, a large language model, and an autoregressive flow-matching acoustic head. The flow-matching acoustic head operates over a 48 kHz audio VAE. So instead of predicting discrete codes, the model is predicting in a continuous latent space all the way through. The audio VAE handles the continuous audio representation. The benchmark numbers from their official page are strong. On Seed TTS Eval, the standard TTS benchmark, they hit the best average performance. WERs of 0.94% on Chinese, 1.30% on English, and 6.60% on Chinese hardset. The demo page shows context-aware expressive voice cloning. The model adjusts prosody and emotion based on the context of what's being said, not just the reference voice style. Apache 2, weights on Hugging Face, Playground on HF Spaces. If you're interested in reading further, I'll link to the demo page in the description below. Also this week, Google DeepMind just won the CVPR 2026 Best Paper Award with D4rt, and the name says exactly what it does. It sees the world in 4 dimensions. 3 spatial, 1 time. Here's the problem it's solving. If you have a video of a dynamic scene, people moving, objects changing position, reconstructing what's actually happening in 3D is extremely hard. Current approaches typically handle depth estimation, motion tracking, and camera parameter estimation as separate problems with separate models. They're slow, inconsistent with each other, and can't generalize easily to new scenes. The result is 3 unified capabilities from one model. 3D tracking predicts sparse 3D tracks for specific pixels across frames. 3D reconstruction projects full depth using camera pose with dynamic objects correctly deduplicated. All pixels tracking, the most impressive one, produces a holistic scene reconstruction by predicting the 3D tracks of every single pixel in the video simultaneously in world coordinates. The project page has interactive 4D reconstructions you can click and drag to rotate. You're seeing the full point cloud of a dynamic scene, and you can orbit around it and see both the depth structure and the motion paths. Best paper at CVPR 2026. If you're interested in reading further, I'll link to the project page and the DeepMind blog post in the description below. Also this week, Tanker launched, and the pitch is simple: GitHub for robots. Robotics development is uniquely messy. You're not just writing code. You've got hardware assembly instructions, CAD files, sensor integrations, operating software, training datasets, and the models themselves, all separate, all in different places, with no standard way to package and share them. If you want to reproduce someone else's robot build, you're hunting across GitHub, Google Drive, a lab website, and a Discord server. Tanker puts all 4 layers in one place. Hardware, step-by-step assembly instructions with bill of materials, connected to Onshape and SolidWorks. Software, documented control systems, sensor integrations, and robot operating code. Data, operational data sets, collected from the robot community that feed directly into training pipelines. Models, deploy and test vision language action models directly onto your hardware from the same interface. The standout feature is something they call Leonardo. It's an AI that watches your first-person build video and automatically generates step-by-step assembly documentation from the POV footage. Record yourself building the robot, and Leonardo turns that into a structured guide other builders can follow and ask questions about. Projects on Tank right now include humanoids and quadrupeds. It's live at tanker.ai. If you're interested in reading further, I'll link in the description below. Also this week, Mama is a CVPR 2026 oral from the Max Planck Institute for Intelligent Systems. And this is the kind of computer vision paper that feels practically important for robotics and animation. Mama stands for Markerless Accurate Multi-Person Motion Acquisition. The problem it's solving? Traditional motion capture requires actors to wear suits covered in reflective markers. Expensive, complex, limits where you can film, and completely impractical for spontaneous human interaction. Markerless motion capture exists, but existing approaches break badly when 2 people are interacting closely, hugging, dancing, contact sports, because the bodies occlude each other, and the methods can't handle the ambiguity. Mama introduces 2 key things. MamaNet, a transformer-based dense landmark estimator that predicts 512 surface landmarks per person from a multi-view video. Critically, it doesn't just predict pixel coordinates. It also predicts uncertainty, visibility, and contact probabilities, person-to-person contact, and floor contact. Those contact signals are what allow the system to handle tight interactions without physical impossibility, 2 bodies intersecting each other. MamaSyn, a large-scale synthetic dataset with 2.5 million crops, extending the Bedlam dataset to a multi-view setup with higher resolution rendering, specifically covering extreme poses, high-fidelity hands, and complex multi-person interactions. The demo videos on their page show MamaNet handling extreme yoga poses, splits, inversions, overhead positions that would completely confuse a model without learned per landmark embeddings, and still outputting accurate landmarks. And for 2-person interactions, the contact optimization step produces physically plausible results. If the model predicts contact between 2 people, it actively prevents their body models from interpenetrating while encouraging realistic contact geometry. Code and data are available on GitHub. If you're interested in reading further, I'll link to the project page in the description below. Also this week, Alibaba's Quen team dropped Quen ImageBench, and this one is a tool rather than a generative model. It's a judge. The problem? Evaluating text-to-image generation quality is genuinely hard. You can run clip scores, you can run FID, but those don't capture what humans actually care about when they look at a generated image. Existing automated judges either correlate poorly with human preference or for our closed source. Quen ImageBench, internally called QJudger, is an open-source judge model built on Quen 3.5 that evaluates generated images across 5 dimensions: quality, aesthetics, alignment, real-world fidelity, and creative generation. Each image gets a structured score per dimension. The raw scores are mapped to a normalized scale and then aggregated. Their paper reports high human agreement on the scoring, meaning QJudger's ratings match what human evaluators would give. It's Apache 2.0 running on Hugging Face right now. The idea is that you use this to evaluate your own image generation pipeline locally. No API dependency, no closed source judge. If you're interested in reading further, I'll link to the model page in the description below. Also this week, Microsoft released Vibe Voice, and this one is specifically for long-form, multi-speaker audio, the kind you'd use to generate a podcast. Standard TTS systems do single speaker, short outputs, and they break down over long sequences. The voice drifts, the pacing gets robotic, turn-taking sounds unnatural. Vibe Voice is built specifically for the opposite. Up to 90 minutes of audio, up to 4 distinct speakers simultaneously, with natural turn-taking and consistent speaker identity throughout. The core architecture: continuous speech tokenizers, both acoustic and semantic, operating at an ultra-low frame rate of 7.5 Hz. That frame rate is the efficiency key. 7.5 tokens per second is dramatically lower than typical audio tokenizers, which lets the LLM backbone process long sequences without exploding in compute. An LLM handles the textual context and dialogue flow, and a diffusion head generates the high-fidelity acoustic details. The demo audio clips on their page show exactly what this can do. There's a 2-person argument clip with spontaneous emotional shifts. The speakers argue, and the prosody reflects the emotional escalation naturally. There's a 2-person clip where one speaker spontaneously starts mid-conversation. There's a 3-person podcast clip with background music layered in. And the most impressive, a 4-person climate discussion podcast running at 45 minutes and again at 100 minutes, with all 4 speakers maintaining distinct voices throughout. There's also a cross-lingual demo, Mandarin to English and English to Mandarin voice transfer, where the voice identity carries across the language switch. One thing to flag: Microsoft's own GitHub page notes that after the initial release, they discovered the tool was being used in ways inconsistent with the stated research intent, impersonation, and other misuse. They've since disabled the GitHub repo temporarily while they work on safeguards. The demo page is still up, and the audio samples are there. If you're interested in reading further, I'll link to the project page in the description below. And last but not the least, HumanoidGPT is a really impressive robotics paper out of Tsinghua University and Galbot, accepted at CVPR 2026. And this one is specifically about solving the fundamental trade-off in humanoid motion tracking, the problem they identify. Current humanoid motion trackers face what they call an agility generalization trade-off. You can either train a model that tracks agile, dynamic motions, like dancing, high kicks, acrobatics, but it only works in domain. Or you can train a model that generalizes to unseen motions, but it's slow and conservative. Nobody had combined both until now. The key ingredient? Scale. They assembled a 2 billion frame motion corpus by aggregating every major motion capture dataset, plus their own large-scale in-house recordings. For context, the previous best baseline, Sonic, was trained on 100 million frames. HumanoidGPT has 20 times more data. The model is a GPT-style transformer trained via dagger distillation from motion experts. It runs on a Unitree G1 humanoid robot. The demo videos on their project page show the robot doing daily motions, dance moves, high dynamic motions, and balance balance tasks, all with Sonic shown on the left and HumanoidGPT on the right for direct comparison. The difference in smoothness on dance sequences and stability on balance tasks is obvious. The inference is optimized with Onyx and TensorRT. End-to-end latency under 1.5 milliseconds on a single RTX 4090. That's approximately 5 times faster than Twist, the previous inference speed leader. And they demonstrate clear scaling laws. More data and more model capacity both consistently improve tracking accuracy, which means this approach has headroom. If you're interested in reading further, I'll link to the project page and the archive paper in the description below. And that sums up the key AI news for this week. Which of these was your favorite? And which are you most looking forward to trying out? Let me know in the comments below. As always, I will be on the lookout for the top AI news and tools to share with you. Remember to like, share, subscribe, and stay tuned for more content. Also, there's just so much happening in the world of AI every week. I can't possibly cover everything on my YouTube channel. So, to really stay up to date with all that's going on in AI, be sure to subscribe to my free weekly newsletter. Thanks for watching, and I'll see you in the next one.